Yeah, so this is our final choice, right? So we started with 110 dB. So we decided that order of 4 with 1.35 OBG with single bit is enough. So oversampling ratio is 128. So I chose my bandwidth to be 24 kilohertz. So my actual sampling rate is the Nyquist sampling rate, which is 2 times the bandwidth times oversampling ratio, that's around 6.144 megahertz. And I mean, the second thing is you also need to figure out what is your maximum stable amplitude. So I can quickly check it, because here I have actually found out the SQNR for different amplitudes, right? So I'll basically plot the amplitude versus SQNR. Okay. So you can see, right? So ideally in a normal ADC till 0 dBFS you should be able to apply. But here, you know, in delta sigma, the actual signal going to the quantizer also contains the quantization noise. So your maximum stable amplitude will be smaller, and that's around here, yeah, 3 to 4 dB. So you can only apply 3 to 4 dB lower than your full scale. Okay, and that if you calculate, it comes out around 0.6. So roughly 0.6 times the full scale, which is the supply. That's your amplitude. So that's how we do, right? And to summarize, basically you choose your signal to quantization noise ratio, usually to be larger than your overall thermal noise limit. And of course you have to start with some choice. One thing to remember is this: if you have a third order with a single bit OBG of 1.5 with 64 OSR, you can get around 80 dB of SQNR. From this we can basically tweak out depending on your requirements. Now for changing SQNR, you have all these size. You can change the OSR. Right now we have fixed that we are using a single bit quantizer, but you can also increase the number of levels in quantizer. You can also increase the order and OBG, right? We saw what happens when you increase each of them in the last class. So based on how much you want to increase the SQNR by, you can tweak either of them. If you want to change it by a large amount, your nice bet is to change the OSR. For small changes, you can do either of the last three. Is that okay? So now we have gotten what is your NTF. So once you have the NTF, the next thing is to go and design the loop filter. So let's quickly see what will happen. So let me draw this guy. So again, what is NTF in terms of the loop filter? 1 by 1 plus L of Z, right? So what is L of Z in terms of NTF? Okay. Now you guys know if NTF is 1 minus Z inverse, what is my loop filter? It is just one integrator. Okay. Now let us say let's move to second order. If it is 1 minus Z inverse whole square, this is my NTF. For a first order NTF, the loop filter is one integrator. For a second order NTF, what do you think the loop filter will be? I mean, just take a guess.
If the form is 2 Z inverse minus Z inverse square.
Yeah, I mean, yeah. Basically, see, let's not find the exact thing also, right?
Okay.
Loosely speaking, for a first order NTF, the loop filter consists of one integrator. For a second order NTF,
You've got
two integrators, and that should also make sense logically, because for small values of omega, how does the NTF go as? Omega square. And if I look at this guy, for small omega, how does this go as? I mean, 1 minus Z inverse for small frequencies, how does it go as? Omega. So how will this guy go as? I mean, this guy goes as omega, you know.
Yeah.
Now we have 1 by that quantity. So how will that go as? 1 by omega, right? Is that okay? And remember, it's just integrator, right? Integrator is 1 by S kind of thing, right? It will go as 1 by omega. So if you have two integrators, how will this go as? 1 by omega square. So at low frequencies, if you have two integrators here, For low frequency, this will go as 1 by omega square, right? And you are adding the quantization noise here. So if I refer the quantization noise back to the input, I mean, remember that to find the quantization noise at the output, I can as well find what is the effective quantization noise when you refer it to the input, because the STF from input to the output at low frequencies is 1. Is that okay? So if I refer this guy back to the input, what will it be? I have Q of e power j omega.
Omega square into this.
Yeah, and before that I have a block which has a gain of 1 by omega square. So if I push it back, it will be divided by that gain. So it will be Q into omega square, right? Just divided by that gain. And remember, this is what your NTF is also, right? You want an NTF at low frequencies to be omega square, right? And to get that, you need to have at least 2 integrators. Only then the NTF will be of the required form. Okay. And in this case, you can actually find what the loop filter is. It's 1 by NTF minus 1, and you can work out this thing. Yeah, something like this. And in fact, you can write it like this. You can decompose this as K1 times 1 integrator plus K2 times cascade of 2 integrators. The same thing, can decompose it like this. Okay. So let me just extend it now. So now let us say you have 3 integrators, that is not 3 integrators, sorry, NTF is this guy, 1 minus E inverse whole cube, right? For a second order NTF, the loop filter looked like this. For a third order, how do you think it will look like?
Third order, there will be K3 term.
K3 times?
The three like that inverse upon 1 minus
Right?
Z inverse the whole cube.
So you'll have K3 times Z inverse by 1 minus Z inverse the whole cube. Okay. Cool. So now let me ask this question. Yeah, so can you tell me what will be this value of K3 here? Why? This guy, you're saying it's 1, right? Why is that so? Okay, I mean, okay, instead of doing that, right? I mean, you don't know, right, exactly, because if you do this, you'll get some complicated expression. This you have to decompose, and it turns out it is 1 actually, but qualitatively, do you think it makes sense? Okay, maybe I'll lead you to the answer. So again, let's do the same thing. At low frequencies, how will this go as?
Omega square.
No,
Omega
omega
cube.
cube,
Yeah.
right? And how will this guy go as at low frequencies?
K1 upon omega plus K2 upon omega square.
It will go, but
Plus K3
I mean, at low frequencies,
this
okay.
term, the last term will be dominant.
They're okay. For low frequencies, it is still K3 by omega cube, right? So this is going to be what now? At low frequencies, this goes as K3 by omega cube. So if I refer it to the input, what do I get? Omega cube by K3 times Q of e power j omega. And remember, this is my NTF, and your NTF must be this. So what is K3? K3 must be 1, right? That simply comes because at low frequencies, you want your noise transfer function to go as omega cube. Okay, so that will simply dictate the coefficient of the cascade of 3 integrated parts to be 1. Is that okay? So then let's extend this. So now let us say I don't have this because I want to change the OBG. So now let us say I have an NTF which looks like this. So at low frequencies, how will this go as? Yeah, what is alpha? Can you? Omega cube by d of? So now what is K3? Huh? Same thing, right? So this is now your NTF, and this is the NTF here. So just compare it, you will get K3 to be equal to 1. So this is something you should be able to deduce straight away. Right? Cool. So okay, then that probably should make you ask this question. If not, I will ask it myself. So here, if you look at it, my loop filter comprises of 3 parts, right? So I'll redraw it slightly then to show the 3 parts explicitly.
Do you want delay?
No, let me just come there. Hold on. So let us say this is k1 times 1 integrator I. This is k2 times 2 integrators I square. k3 times 3 integrators I cube. And oops. And everything is summed up here, right? Now, my only goal is to keep an NTF which is of this form. At low frequencies, I want my NTF to behave like this. That is my only goal, right? And this is being enforced by which of these 3 parts here? We have the third part. Is that clear? So this guy, I'll call it as the accurate path. This is what is making sure that my low frequency quantization noise is shaped by omega cube times the required factor, right? So that should make you ask the question, if this is the path that gives me the required shaping, why do I even need these 2 guys?
It's only for
Make STF ones?
No, not really. I mean, STF being, see, the STF is 1 at low frequencies simply because
That is gain is higher.
yeah, I mean, if you have any negative feedback loop, if this guy has a large enough gain, then the transfer function from here to here is approximately 1.
Here also, yeah.
Right? What were you saying?
like K3 guys, that's accurate only during low frequencies.
Okay, it's indirectly correct. So, I mean, that's what you also want, right? You want the quantization noise at low frequencies to be shaped by omega cube. That's how we started this entire noise shaping business. And looks like I can get it done only by this fellow, right? So question is, why do you need these 2? Your statement is indirectly correct, but
Is there anything with the delay?
yeah, what will happen to delay?
Means I-Q1 will take a lot of time.
Correct.
But I and I square will be giving normal answer, not accurate answer.
Yes,
But
correct. So yeah.
in a long time, the answers will much more stability.
Yeah, I mean, people have taken some control should be able to say, right? See, ideally you want this guy alone, but as he pointed out, this is going to have a lot of delay, right? Basically, let us say you assume that these guys don't exist at all. Your negative feedback is only from this guy. Let's say erase this guy for now, right? If you have only this guy, then if you make if any change happens at the input side, for the feedback to come, there will be a lot of delay because we have 3 integrators here. This loop filter will take a lot of time to give the feedback, and the moment you have long delay in your feedback loop, it can become unstable, right? That's why what you do is to have these paths. These are fast but inaccurate paths. We'll say quick and dirty estimate, right?
This will be in 613 also, right?
Yeah, this is basically 613 or I mean any control systems, right? This is your proportional path. Why do you need the proportional path? You want a quick and a dirty estimate. You don't want the feedback loop to be waiting for some response. You give some quick and dirty response to the feedback path so that the loop is stable. So these 2 paths will have very short delay. So any change at the input, you will get quick response here. So which means the feedback will also come fast. So the loop will get stabilized. But in long term, this is what will dominate because this is what will give the final noise shaping. Okay. So these 2 parts exist only for stabilizing the negative feedback. Okay. Cool. So in that case, then can you comment on this? We will not erase this. Yeah. So yeah, you know the value of K3 here. So can you comment on K3? Now can you tell me if K1 they'll be smaller than K3, greater than K3 or equal to K3. From this understanding, you know that this K3 path is going to have a long delay. If you just wait, if your feedback loop is only dependent on this guy, there is going to be definitely instability. So you need to have a fast and dirty path, and that is what is being provided by these two guys, right? So for stabilizing this loop, this guy must be responding, right? So if that is the case, can you comment on the relative values of K1, K3?
K2, right?
Let's say K1 and K3. Let's
Okay.
Sorry, which should be greater?
K1.
Why?
So that it will dominate.
Yeah, that's all right. See, you want any change at the input. You don't want the output to be dominated by this guy. You want a fast and a quick estimate from the fast path. So you want to make sure this gain from the fast path is much higher. Only then the feedback will be stable. Okay. So usually you'll find K1 will be much greater than K3. Okay. Cool. What's the time?
Sir, it's inaccurate.
Correct.
We are making K1 greater than K3.
Yes, but greater than K3, but finally if you see the gains, you have K1 by omega and K3 by omega cube, right? This omega cube will, in the long term, it will give much larger gain, right? But to instantaneously stabilize the feedback loop, you want this path to be much faster. So, I mean, you can think of it like this. This is adding a 0. The proportional path will add a 0 usually, right? You want to keep the 0 at a sufficient frequency so that your loop is stable in control theory. But intuitively speaking, you want the fast path to be dominating the slow path for instantaneous changes. So, cool. So that's about the loop filter, and it turns out this loop filter can be implemented in a couple of ways. I'll just show one commonly used thing. The other thing I'll give it as an exercise for you to work out, and the one way in which you can do is what is called cascade of integrators. In feed forward or CIF. It's simple. So we have three integrators, let us say. I'll just say it's I, and I. So what you do is you take K1, that's all, right? And then you can add these two.
Feed forward compensation.
Yeah, so this is basically the integrators are cascaded obviously, and to get the individual outputs of each integrator, you are doing the addition in a feed forward manner. You can also do it in a feedback fashion. I'll give it as assignment, but this is more commonly used, and then you finish the loop. So here again my STF, what will it be? If I call this guy as L, this entire thing as L, right? What is the STF? Yeah, I mean it's L by 1 plus L, and it turns out if you actually sketch this at low frequencies it is 1, and turns out at high frequencies it will show some peaking like this. Okay. So in order to avoid this peaking at high frequencies, and also for another reason which I will not discuss in detail, what we do is this. Along with the usual stuff, you take the input and add it directly here. Okay. So let's see what will happen to STF now. So help me find the STF. Again, we'll assume that this entire thing is L of Z, right? This portion entirely is L. So for simplicity, maybe I'll erase this portion. This entire thing is my L of Z. Right. Now can you help me find the signal transfer function? I mean you can write everything and work out, but qualitatively can you compute? I mean ideally you had input, usually you give the one input only to one path.
One way.
Yeah, basically you can think of it as two inputs, right? Linear system. So what do you do? Superposition. I'll assume this input is not there now. This is 0. If this is the case, what is STF? L by 1 plus L. Now the other path is active. So let us say now this is 0 and the input is applied here. What is the transfer function when you add a signal to this point and you measure the output here? It's the same as the noise transfer function. So it's 1 by 1 plus L. So what is STF? It's exactly 1. So this will make sure that this peaking which you would have had normally, it's completely gotten rid of. So another nice thing about this is this. I'll mark this fully. So you know that the output is going to contain the input directly, right? Exactly 1 STF. So which means here also I'll have the same input U. So what can you say about the signal content here? At this point. I mean, point is, let me maybe write in different color. See here I know that the, I know that the STF is exactly 1. So which means that the output I'll get exactly U, ignoring quantization. So which means even at the input of the quantizer I should get the same U. Now question is, what will be the signal content here? 0. Why? Because, yeah, I think you get it, right? Because this input is given directly from this path. So the U content is directly coming from here and this need not contain any signal. Right? So which means your loop filter will not contain any signal swings at all. It turns out in transistor level implementation this has some benefits. Let's not get into that.
In this, what is the error signal it's making?
Same thing, right? It is U and this V.
Because if that this path is 0,
I mean, see,
the entire
see,
function was 0, right?
see, this ideally contains NTF times Q, right? For considering only the signal path, I have ignored quantization noise. I mean, notice that this adding this is not going to change anything to my NTF, right? Because the entire thing starts from a particular NTF. You design a particular NTF, from this you find a loop filter. And for a particular NTF, you just need to make sure the transfer function seen by the quantization noise, the transfer function seen from quantization noise to the output is this guy. That's all, right? As long as you use the correct L here, your NTF is set. Whatever I am doing here is only changing my STF. That's all. Is that okay? Cool. So maybe 10 more minutes will be. So yeah, cool. And again, you don't have, I mean here, you know that your L of Z, you have to decompose it like this: K1 times 1 integrator, K2 times 2 integrators, K3 times 3 integrators. These values of K1, K2, K3, again you don't have to compute, you can get it from the toolbox. Right? So once you get it, again you just have to implement the circuit. So let's look at how we can implement the circuit, right? So let's start with a simple first order. You guys know everything, we just have to put things together. Let's quickly do that. For a first order case, what is the loop filter? Is that okay? Z inverse by 1 minus Z inverse. And let us say I take a single bit quantizer here. Right, this is my U. And how do you implement this in circuit? The delayed switch capacitor integrator. So you have this guy. Let us say, I mean, first let's implement only this fellow. This is this, and then in second phase you do this. And the output you sample it in phi 1 again, so that you get the delay. Is that okay? But here I have to subtract the input and the output V. So how can I change this? This is integrating the input only, right? Now I have to integrate the difference of input U and another signal V.
Instead of this 1 ground, put it V.
This we saw in pipeline ADC case also.
There? Yeah.
Where do you want to put? This you can't put because remember that the feedback will not be available instantaneously for you. You are saying you put, where do you wanted to put? Here, right? Yeah, this is in principle it's okay, but in practice V will not be available instantaneously, right? Here first your input has to be sampled, integrated, and it will come. So you put it here. Is that okay? I mean, if you do this, see in phase 1 you are sampling the input in this capacitor. The charge in the capacitor is what if this is C? In phase 1, C times U. In second phase, what happens? You are connecting this to V. So what is the charge stored in the capacitor? This is virtual ground, remember?
Yeah.
At the end of the phase phi 2, what is the charge stored?
CV.
C times V. So what happened to the remaining charge?
Went to the
And what is that remaining charge?
CU minus CV.
C times U minus V. And this charge went here. And that's how the integration happens. The difference is getting integrated. Is that okay? So okay, and again this V is basically your feedback signal, and remember if the output is some DO, digital data, you have a DAC ideally actually. If it's a single bit, if DOut is 0 you want to connect 0 here, if DOut is 1 you want to connect some VREF here. So how can I do that here? I mean V can take only two values, 0 or VREF, and it depends on the digital data DOut. So how can I make this here? Yeah, we have two switches, we saw it in pipeline also. So you have VDD, this is when DOut is 1, you connect it to ground, okay. Cool. And remember this has to be given to the, yeah, this is that same we saw in pipeline ADC also. We are using the same capacitor for realizing the DAC also, right? So this is, I mean ideally, yeah, this comparator goes here. So here now the comparator is sampling it in phi 1. So in which phase it can do the comparison? In phi 2 is when it can do the comparison, and in phi 2 itself this has to give DOut, and this DOut will control this. Okay. So if you had to draw a timing, it will look like this. So let us say phi 1, phi 2, phi 1, phi 2, phi 1, phi 2. So let us say here is when the input is sampled, here it is when it is integrated. At this edge the comparator is sampling it, and the comparator should make the decision here itself quickly, and during this phase the feedback should happen, right? I mean you can also slightly modify it to relax some timing, because here you see that the comparator has to make the decision immediately and the same thing should be fed back. To relax the time, one thing you can do is this. So I mean I just need to, I want the same thing to happen, right? I want if the input is sampled here, I want the feedback to come here. That's what I want. So I can slightly massage some timings. I can sample the input in phase 2 itself. That is, I can make the comparator sample the input here itself. Because remember at the end of this phase my integrator is ready. So I will make sure my comparator samples here itself. So which means I have so much time for regeneration. I can have 1/2 clock cycle for the comparator to do the decision, and in the next phase I will do the feedback. The only thing you have to make sure is this: if I sample the input at this point, the feedback should happen before this, before this point.
Why did you do this?
To relax the timing, right? Okay, hold on. So only thing I want is if the input is sampled at this edge, the feedback should finish here. This is the only constraint I have. Okay. In the earlier case, what we are doing is the input was sampled here, the feedback finished here, but the way we had it was the comparator was sampling it at this point, and it had a very small time to regenerate, and it has to regenerate instantly, and the feedback should also happen in the same phase. We had the same clock phase for comparator's regeneration and the feedback, which means if the comparator is taking long time, the feedback might not finish, right? Because remember that this guy should control these switches and this should transfer the charge. Okay, but if you do the other way, you can slightly advance the intermediate operation, wherein I can keep the comparator so that I can sample it here itself, so that this entire clock phase is available for regeneration. Then I can do the feedback here.
Will that LZ be the same if you put?
Yeah, that's okay. I mean, that's what we want, only this to be satisfied. We want only the feedback to be correct.
We want the pole.
Yeah. Just think about it. It's just minus 2. Okay. Cool. And in fact, if you now you should go go back and check your midsum question paper. So there, if you remember, there was one question on charge conservation, and you were asked to find the transfer function, and the result was 2 into 1 minus the inverse. Now they should strike something. Does it resemble something?
NTF.
It's an NTF. Now we can go back and check. It was basically a circuit like this, and then I added some gain somewhere, and then did this. I think some gain of 2 was added somewhere. I think here or there. I don't know. Right? A gain of 1, but somewhere a gain of 2 was there. I forgot. You can check out. Right? I mean, so there the only difference was here I am making sure that the input and the feedback is integrated on the same capacitor, right? Sample on the same capacitor. In that question I had different capacitors, that is, I had one capacitor for the input sampling, I had another capacitor for the integrator, I mean for the feedback. This is U and here the V was there. Oops. Yeah, so I had another, oops, sorry, what is this? Something like this was there. Something was put here and then okay. Now we should go back and check and try to at least make qualitative sense of what the circuit is, right? You don't have to now sit and solve using charge conservation. You should be able to now look at the blocks and understand what that block is, and then draw some equivalent model like this and do. And in fact, even in your practice problem set, I think I made you calculate the signal transfer function. That's why I think you got it as Z inverse or 1 somewhere. In one of the practice problem set, this was what was asked.
Yeah.
And that was basically same first order delta sigma modulator with the transfer function asked from the input to the output. And this is not there. Okay. So, cool. So we'll stop here.